Welcome to the second course. So now we're going to start new stuff. So what I want to talk about this week is lazy evaluation, which is an important approach for functional programming. So this is still declarative functional programming. So we're going to, in the next couple of weeks, show you a lot of powerful techniques in declarative functional programming. These techniques will also work for the other paradigms. All the techniques in functional programming also work for the others, but they have the extra advantage that they have the power of declarative programming. So before I start, I want to emphasize that this course this year will not have very many slides. I will write on the board, and most of the material is in the textbook, this book. So this is very important. And so what we're going to see today is in section 4.5. Most of it is in section 4.5. There are a few things I will say on the board that are not in section 4.5. So you will see that when I give the semantics. So in fact, this book was published in 2004. So now we're 16 years later. So the semantics I'm going to give you now is a better, simpler, more powerful, cleaner semantics than the one in the book. Okay, so this is improved. So I will give some new things that are not in the book, extra things that we learned in the last years since the book was published. So not everything in it is in here, but most of it is in the book, is in the textbook. Okay, so this is important. Another point is that I'm going to write some code. And I will put the code on the Moodle, so you will be able to see the code that I write on the Moodle. So let me start with lazy evaluation. Let me start by giving you an example. So here is the Oz system, which I hope that everyone can see. Normally the people at distance can see also. So let me show you first an example of a lazy function. And then we'll see how it works. This is a function that's very simple. It will add two numbers together. Okay, lazy add. And it looks just like a function, except that I annotate it by lazy. So I will first show you what it does, and then we will look at the semantics, and then I'll show you all the powerful techniques you can do. Now, if I do now something like this, lazy add 10 and 20. Okay? So I'm calling the function. And now I browse S. And I don't see the result. So when I call a lazy function, I create a kind of object called a lazy suspension, and the function is not evaluated immediately. So what happens? It's only evaluated when I need the result. So browsing, the browser is a special tool. It will display things as they are. It does not need the result. So what does it mean to need? So I will show you a simple example, and then in the semantics we'll be more clear on that. So it will only display S when we need the result. So how do we need S? Well, one way to need S is to do a computation. So if I do S plus 100, so the addition operation at the plus needs its two arguments. So this will cause the function to be evaluated. So the function will only be evaluated when you do the plus. So when I do the plus, I will see that S is needed, and then I will evaluate the function, and then I can execute the plus. So when I execute this, I will display S, but also S plus 100. Okay? So 30 and 130. So you see, it's the need that drives the computation. So that's a very simple idea, but it's incredibly powerful, and we're going to see all the consequences of this in this today course. So let me first give you the semantics of this. Let me go back to this. I'm going to write on the board. So the semantics of this. Semantics of lazy evaluation. Let me refresh your memory first on the semantics of the data flow. Computation of deterministic data flow. We have two operations called weight, x, and we have bind, x to a value. So the weight x will suspend the thread until x bound. And the bind x will release any waiting weights. Okay? Weights to continue. So these are the two primitive operations that define the data flow. Assume now that I want to do an addition. C equals A plus B. Okay? Well, the semantics of this plus will do a weight. So this is compiled as follows. It will do weight A, weight B, and then a primitive add operation, which, for example, does V is equal to A plus B, and then a bind. So whenever I do an operation that has a data flow semantics, like plus, or the case, or the if, or whatever, many built-ins need wait for values. So I wait until A is a value, I wait until B is a value, and then I do a primitive addition. So this is an addition in the architecture, in the machine. Okay? So the primitive addition assumes that A and B are values. If they're not values, there's an error. This one assumes that A and B are actually numbers. And it will bind V to the sum of A and B, and then I will do a bind operation. So if I do now a data flow operation, if I have something like C equals A plus B, and then D equals C plus 5, okay, then there is a data flow connection between these two. So the first one will eventually do bind of CV, okay? And the second one will do a wait on C before continuing. You see? And this one will eventually do a bind of D with a new value. So this data flow connection is done by the bind and the wait. So you see how it works, huh? So if this is executed in its own thread, and this one in another thread, then if the scheduler executes this one first, then it will wait on C. And eventually the scheduler will execute the first addition, and it will bind C, and this causes the data flow synchronization. It's the connection between the bind and the wait. Okay, so these bind and wait are primitive operations supported in the virtual machine with those semantics. Okay, so this is the semantics of the data flow. Without lazy. So far we're not doing lazy, yeah? This is something we already saw. This is exactly the semantics of all the data flow we saw in deterministic data flow. And all of the good things in deterministic data flow, Taylor recursive append agents, declarative agents, using Taylor recursive list functions, that do not grow in memory is possible because of this data flow semantics. Okay? So this is a very nice semantics for concurrent programming, and in fact it's now very popular. Most of the large-scale analytics tools based on the original MapReduce are using something like this semantics. So this semantics is today very popular, okay, for data flow. But now I will extend the semantics for lazy execution. Okay, so let me remove the example. I'll keep the weight in the bind. So we will make an extension, or a small extension to this, that will allow laziness. So for lazy evaluation, we add one simple operation to this. One new primitive called weight needed, x. So this one also waits. This one waits for something. Yes? Question?
C'était pour dire que l'écran du PC cache un peu le tableau quand vous écrivez par-dessus. Ouais.
Comme ça?
Oui, parfait.
Désolé.
Non, pas de souci.
Okay, so the weight needed also waits. But it does not wait until x is bound. So basically, it waits on another condition. So it waits until there is a weight x. This one will wait until another thread does weight x. See, it's a little bit subtle, huh? That means that when I do a weight needed for a computation, it will only do the computation, it will only continue if some other thread does weight. So basically, the weight, this is what we mean by needing. So this is what x is needed means. So we say that x is needed by the computation if a thread does weight x. In that case, x is needed, and this one will continue. So this allows us to do some very interesting things. Let's say I have x, I do weight needed x, and I do x is equal to a big computation. Whatever. When I do this in a thread, this will suspend here. If I do browse x, it will display an underscore, because the browse does not do weight. If I do browse x plus 100, then this plus operation has data flow semantics. So this plus operation will do a weight on x. The weight on x means it needs x, and that will cause the x to be bound. So you see, the need for x drives the computation. So it's extremely simple, but it has huge consequences when we start doing programming, okay? So it's very important to understand the difference between weight needed and weight, okay? They're totally different. Let me show now an example. So let me declare x, and weight needed x, and then x is some computation. Okay, now we browse x here. So weight needed is an operation that exists in the system that you can use directly in your programs. You can use it and you can program with it. Okay. So I execute this, I browse x, and nothing is displayed. Underscore. So the weight needed blocks. It suspends. So how can I make the computation be done? Well, I have to need x. So I could just do weight x, huh? if I want, then this will trigger the weight needed. But I can also do something like this. Browse x plus 1000. And you can see that now the x is computed, also x plus 1000. So the addition operation is what triggers the calculation of x. This is totally different from the regular data flow. Huh? Regular data flow, you call a function, it's executed right away. Here it's not executed until it's needed, which means until another thread does wait x. Okay? So those are the primitive operations. Now, the language has some syntactic support for this. If I define a functions, so let's look at functions. So the regular functions, the ones that we know, we call them eager functions because they compute immediately. Fun f of x with some expression end. Okay? And these are translated into a kernel language like this. X with one extra argument r, and r is equal to expression end. So the expression is also translated into kernel. Huh? So this is how it's done, the regular functions. So a lazy function also has a translation with weight needed. So the Mozart system has a syntactic support for this. You annotate the function as lazy, f(x), expression end. So you can see that regular and the lazy function are almost the same. Yes?
You have to move to change the screen because they don't see the boards.
They don't see it? Well, normally the board is the screen is not showing this part. Is what you're saying?
I think so. It's my friend.
Let me see. He tells you that there's not seeing it.
Yeah.
Okay. So where does it cut off? Here? So I know about where, up to where?
I don't know.
Okay, let me make it in the other part. So this is readable, right?
He see the screen of your MacBook, but then the
Petit problème
en fait,
technique.
il voit votre écran de MacBook, mais pas votre tableau.
Ah, ok, je comprends. Oui, en fait, ce que je dois faire, c'est faire comme ça.
Le truc, c'est que je dois
C'est mieux maintenant?
plier pour voir.
Oui, okay, so right, I should have ended the screen sharing. Yeah. So the teams will only show one thing at a time, either the video or the screen. So it's okay now? Okay. So a lazy function has this lazy annotation, and it's also defined in kernel language in a slightly different way. So what happens is, it's going to be defined using weight needed. So it's going to create a thread that does weight needed of the result of the function, so of r. Okay, now of x, and then you have r equal expression end. Here. So you see how the lazy function is translated. So the weight needed, it has to wait. So you know threads are units of waiting. So in the deterministic data flow, we will create a thread to wait on the need of the result. So it waits for r. Okay, the weight needed on r, not on x. Maybe there's more arguments here, right? It doesn't care about the arguments of x. It cares about the result. And when this weight needed continues, then I compute r. Okay? So this is a syntactic shortcut. So you can see there are eager functions and lazy functions. And you can see the semantics of the lazy function is defined using weight needed. Okay? But for the programmer, they look almost the same. Okay? now that we have this, we can actually write. Let's see if there's a question here. It seems to be okay. Let me go back to the program here. So we can use, now we can write lazy functions. So I've already showed you one. Let me show you another function. Let me do a function called ints, n followed by ints n plus 1. If I define this function, declare, if I define the function like that, in n, there's going to be a problem, right? What is this going to do here when I call it? Oh, come on. It's a problem, right? It's an infinite loop, huh? There's no stopping. This is a regular function. So this has an infinite loop. But we can write it as a lazy function, and it will work fine. We call this one lints, n followed by lints n plus 1. So if I write this function, this looks like an infinite loop. But it's not, because when I call this function, it will not execute until I need the result. Okay? So if I say L is equal to, declare L is equal to L ints of 1, this looks like an infinite loop. And it's a potentially unbounded computation. But because of the lazy semantics, it will only execute the part that I need. Okay? So if I do browse of L, it will display nothing. So how do I need this list? Well, I have to do a wait. I have to do some other computation that actually looks at the list. But you can't do addition on list. Let me define another one. Let me define a function, a procedure called touch, which does nothing, actually. You'll see. What does this procedure do? Actually, it does nothing, in some sense. Touch ln. If n is equal to 0, then skip, then I'm done. So skip is an operation that does nothing. Else, recursive call, touch of l dot 2, and n minus 1. So I will basically traverse down n elements of the list. So in the regular eager model, without wait needed, this really doesn't do anything. Okay, what am I doing? I'm just traversing. I'm not computing anything. But in the lazy model, this will trigger the computation of L. So the L dot 2 operation here, L dot 2, there's this dot here. The dot takes a list or a record and the name of a field and returns the field. So the dot needs L. So it will do a wait L implicitly. Okay, the dot operation needs L. So this causes the L ints operation to trigger. That means the wait needed here, the wait needed will be activated, and I will do the recursive call. So explaining it here. So if I look at the translation of L ints, so it looks like this. Now, the actual translation of L ints, N R thread wait needed R, and then I have R is equal to N followed by L ints N plus 1. Okay? So the lints operation, the semantics of lints is this. Using the kernel, basic kernel operations, the thread and the weight needed. So when I call lints of 1, it will do nothing. But if I assume that I do L dot 2, okay? Assume now that I do browse L dot 2 directly. Well, this causes, so the L is the same as the L here. The L dot 2 will cause this weight needed, because this is actually Ella. This is the L actually. If I use the same name of the identifier, this is the result of L ints. If I do L dot 2, then I will be doing a weight on L, and so the weight needed L will go on, and it will say L is equal to 1 followed by L ints n plus 1. But notice it's not an infinite loop, because inside the recursive call, there's another weight needed, okay? So it will only compute one element of the list, and then it will stop again. So if I do L dot 2, it will just make one step. So if I do this, browse L dot 2, then you can see I have 1 bar underscore. I've calculated one element. And the recursive call to L ints n plus 1, L ints of 2, will block again. See, so every recursive call does a weight needed, okay? So it waits for every single element. Now, if I want more elements, let me show you now touch. If I do touch L, and I want 10 elements, this will do L dot 2 of 9, touch L dot 2, 9, and it will keep going n times. So it will force 10 elements of the list to be computed, and the 11th element will not be computed. It will stop again there. So I will only do the 10 elements. So you can see the result here. So I have browse L and browse L dot 2. So the L is 1, 2, 3 up to 10. Okay? And the L dot 2, of course, is 2, 3, 4, 5. And then there's still an underscore at the end. So the L ints basically did 10 recursive calls, and then it blocks again at the end with another weight needed for the 11th one. Now, interesting about laziness, if I do now a touch again, let's say I do touch L5, but I already have computed 10 elements of the list. Well, the list exists now, so the touch L5 will cause no computation to be done. You see, the laziness, the function is only called once, maximum once when I need it. If I do another touch here, then nothing. Of course, nothing. You don't see anything. I'm not browsing anything. So the laziness, once the L is computed, the value stays. It's bound, okay? And if I do a touch again, if I do L dot 2 again, it will do no extra computation. The laziness will only do each function at most once, okay? So if you keep doing L dot 2, it's not going to call the function over and over again. And that's logical, because the weight needed here, this thread only is created once. And once this thread executes, it's done. And so the L is bound, and that's it. If I again do an L dot 2, there's no more thread waiting. So then nothing happens. Okay? So you can see the ideas of how it works. So now, let me show you, but before going on, let me explain a little bit now the paradigms. Let me give you a little bit more theory, and then we'll show some more examples. Okay? So is this clear? Any questions? It's very clear, it's very simple. You understand the weight needed, how the lazy functions work. Okay? But you see, we're going to build lots of sophisticated things on top of this very simple thing. Eh? So it's important to understand the weight needed. Eh? And I know people get confused between weight and weight needed. Eh? Totally different. Okay? Weight waits until it's bound to a value, and weight needed waits until somebody does a weight. So weight needed will suspend until someone else, another thread, does a weight. Okay? So let me give now a little bit more theory here. Let me take one step back. Before showing you programs, let me explain a little bit. Now we have seen the different paradigms of functional programming. We have seen three now, if you count the lazy. Yeah? We have seen standard sequential function programming. If you add to this threads and data flow, synchronization, threads, single assignment, plus data flow, synchronization, then you get deterministic data flow, which is a very nice model, which we saw in the last course. So this one is the concurrency for dummies model, okay, what I like to call it. And now if you add a single operation to that, weight needed, you can also call this by need synchronization. This is sometimes called by need synchronization. Then you get lazy deterministic data flow. So these are all three of these are declarative, and the lazy one is actually a very powerful model, and in a couple of weeks we're going to show some very interesting algorithms in lazy deterministic data flow. Okay?
Il a écrit lazy deterministic.
Let me now start showing you some programming techniques for laziness. Programming techniques. I will first write them down here on the board, and then I'll show the code. So the first techniques, let me first give us kind of summary of the kinds of techniques you can do with this. So you can, of course, you can have techniques that use infinite data structures. With infinite loops. So this makes the code simpler, because you don't have to worry about termination. Okay? So you don't care about termination. Just write it infinitely. It's very simple. And I'll show some nice example of this. So you don't care about termination. That's very nice. Okay? Okay, and then there's other techniques. So the other technique, it's sometimes called push versus pull. This is, or it's sometimes called output driven versus input driven. So when I have a computation, so I have here a box, here's a program, and there's an input, and there's an output. In the usual eager way, you give inputs, and the outputs appear. Okay? So the usual way, this is called input-driven, it's called push. The push is the usual way programs work. But the other way, the opposite way, is called pull. This way, nothing is done until you ask for something at the output. So the control is on the output and not on the input. Okay? So the eager way, the control is here, and in the lazy way, the control is at the output. So you only do computation when you ask for it at the output. So you're pulling things out of the system, okay, instead of pushing things in. And this is a very interesting duality, seeing the difference. You can actually use this in any languages. In all languages. Of course, the syntax, some languages have support. Languages like Oz or Haskell, they support this, support the pull approach. Whereas a language like Java, if you can do pull in Java, but you need to program it. Okay? So the lazy model is actually usable in any language, except that some languages make it harder to use. Okay? But the pull model for real applications is sometimes what you want. Sometimes you want push, and sometimes you want pull. Okay? And we'll see an example of combining push and pull. So this is a typical question in program design. When you're building an application, does it need to be a push or a pull application? Do I need to pull out results? For example, a database where you query the database, it's like a pull. The computation is only done when you ask for a result. It's not done beforehand. But a smart database might pre-compute some important information and combine the push with the pull. So you see, push and pull are fundamental ways of building an application. Okay? So you can see that eager and lazy are very complementary. Lazy is a very natural thing, and in fact, if you don't have lazy, it's like you only have half a system. It's like walking on one leg if you don't have lazy. A real system will be doing both eager and lazy things. Okay? But let me show now an example of this, program example. Let me first make a block diagram here on the board, and then I'll show you the code. I'm going to do a very simple example, producer-consumer example. So if we have a producer-consumer, we've already seen producer-consumer in the deterministic data flow. We have a producer, P, that generates a stream, S, and a consumer that consumes the stream. Now, there's two ways to do this. The eager way, in the eager way, the producer is in control. Producer controls how many things? Controls the computation. And in the lazy way, it's the consumer that controls the computation. So you see, it's a very dual approach. In the usual way, when you do a pipeline, you put things in and they go through and they come out the other side. But in the lazy way, you pull things out. So only things come out so the consumer is controlled. So the termination, let's say you have a termination is controlled here for the eager way, and termination is controlled by the consumer for the lazy way. Okay? So this is kind of abstract, so I'm going to show you the code for this. So let me go now to the stream. So let me first show you an eager producer consumer. Okay? So eager, this is something we've already seen before. So we have a function producer. Okay, it has a number of elements. So let me write some code. So it will create n elements. Okay, so it will create n elements and then it will stop. So the producer controls how many elements. Okay? And the consumer, let me call it sum, will sum the elements. Okay? So it will do something like this if it's a nil, and otherwise it will keep going. So the consumer is the sum. I can call it consumer, right? But it's nice to call it sum. We'll basically use an accumulator and we'll sum all the elements of the list. So you see, the consumer does not know how many elements there are. The producer knows. Okay? So the producer is controlling the size. So if I do something like this, I have a thread. L is producer. Starts with 1. Let's say I have 100 elements. And the sum will be sum L0n. So this is a simple producer-consumer, an eager one. The producer will generate elements, 100 elements, and the consumer will sum them all. Okay? And then I browse the result. So the number of elements is controlled by the producer here, not by the consumer. The consumer does not know how many elements there are. The sum program has no idea how many elements there are. The producer is in control. Okay? That's very simple, huh? You'll see, it's very interesting to see the lazy version. And then here's the result, huh? 5050, the sum of integers from 1 to 100. Now let's do a lazy version. Okay. Fun lazy. Prod A. Now I do this. A followed by prod A plus 1. Again, the producer will make a list. But now the producer does not know how many. The producer is an infinite loop. It just keeps going. Okay? This time the consumer will be in control. Okay? N will be the limit. So it's like this, L dot 1 plus X N minus 1. So here is another version of the sum, but the n argument here. So it takes a list, it has an accumulator, but it has n tells me how many elements I'm summing. If n is 0, the result is x. Otherwise, I do recursive call, L dot 1 plus x, n minus 1. Okay? So basically, the number of elements is known by the consumer. Okay? So let me show you how this works. So I don't actually have to put it in a thread, but I can. L is prod 1. L0, 100 elements. So the code is almost the same, except that the 100 is now sitting at the consumer and not the producer. The consumer is now controlling how much computation is done. Okay? And not the producer. Oops. So let me execute this. So it's going to give the same result. It gives the same result. So the final result is the same, the two. So the eager one, the control is at the producer, and the consumer, the lazy one, the control is at the consumer. You can see how you can see that it's interesting, huh? It's another way of writing applications, but it's very natural. There's nothing artificial, and the code is very simple. Notice that the sum code here is actually not lazy. It's not a lazy function. So this one will be executed immediately. It could be lazy. If I make the sum lazy, then I would have to pull out the result after, okay? But I can write it in this way. So the producer is lazy, but the consumer, the sum, actually will take these elements and will do its computation. It will not wait until somebody needs it, okay? I'm doing it directly. So you can see it's very reasonable, it's quite okay to put to make like a lazy function be the input to an eager function, okay? So that's a simple example. Let me now show you a more sophisticated example of an infinite data structure, okay? So this producer-consumer example here, you can generalize it to pipelines, and after the break I'll show you a more sophisticated combination of eager and lazy called bounded buffer. Actually, it's a very simple concept that you already know. In networking, you already do it. But maybe you don't realize that a bounded buffer is actually a combination of eager and lazy computation. And it's good to control the lazy computation, okay? So now, let me give you now an example of an infinite data structure. I've already shown you one, the infinite list, but that was a very simple one. Let me show you a more sophisticated example where if you don't use lazy, it's actually much harder to program, okay? So let me formulate a problem. This is actually a famous problem called the Hamming problem. And in the time when this was formulated, so this was formulated by Richard Hamming. Maybe you heard of this guy. He's actually very famous. He did Hamming codes. He also did Hamming windows in signal processing. And he did this. So he did many things, this guy. So the Hamming problem was a programming problem that he presented in the 1950s. And in those days, it was very hard to do, okay? This was like research question, okay? So assume that you have numbers of the form 2 to the A, 3 to the B, 5 to the C, where A, B, and C are integers greater than or equal to 0, okay? Numbers of this form. In the general formulation, actually you have n primes here, but we'll just do with 2, 3, and 5. That makes the example a little bit simpler for writing it on the board. We need to write them in order of increasing size. Until reaching a given limit. But the limit is not known in advance. That means I want numbers of this form. So I start with 1, okay? The next one will be 2. 2 to the 1, 3 to the 0, 5 to the 0. The next one will be 3, and then 4, 2 squared, and then 5, and then 6. 7 is not there, then it'll be 8, and it goes on. 9, 10, 11 is not there, 12, and so on. So I want to generate this sequence until I reach a given limit, maybe 1,000 or 10,000. But I don't know the limit in advance. So the question is, how do you program it? How to program this? So it has to be simple program, and it has to use as little memory as possible. So there's a resource issue. And this is very this is a very important condition. If I'm generating elements, it gets bigger and bigger. So how do I make it so I use the least amount of memory and computation? But memory, if I want to generate up to 1 million, but I don't know in advance, maybe I only want to generate 1 to 1,000. But if I want to generate more elements, how do I do it? If I allocate an array, for example, of a fixed size, it only works up until the array is full. And when the array is full, I have to reallocate a new array, and I waste a lot of time, and it's complicated. Okay? And maybe the new array is also too small, so I'm going to do a lot of overhead if I guess wrong what is the size. But the size, the limit, it's not known in advance. And maybe it depends on something. So I'm asking for elements, and elements keep coming, and I stop when I have the right number of elements. Okay? So how can I program that with the least number of resources, and a simple program? So this kind of program, when you don't know the limit in advance of a sequence that is potentially infinite, there's no limit here, and you don't know in advance, so that's an important condition. Whenever you do a computation where you don't know in advance how much you need, you only will know when you start running things. Then you need to see how it goes. This is typically a program that you can do very well with lazy evaluation. So whenever you have an application where you don't know in advance how much you need, you have to have an alarm bell ringing in your head and saying, maybe I should use lazy evaluation for this. Okay? Okay. So let me do now a small break, and we solve this problem after the break. But let me first show you an algorithm for solving the Hamming problem. So for the Hamming problem, let's construct the list inductively. Let's construct it incrementally starting from 1. Okay? So how do we figure out what is the second element? Well, there's 3 possibilities. It's either 2 times the previous element, because one of these numbers, A, B, and C, will increase by 1, or 3 times the previous element, or 5 times. So in fact, I will multiply this sequence by 2, by 3, and by 5. This gives me 3 sequences, 2, 3, and 5. And then I will look at these 3 sequences, and I will take the least, the smallest one. So here I will put in a 2. Okay? So I put in a 2, and when I do that, the sequences get updated. This one becomes 2, 4, 3, 6, 5, 10. And the 2 here, I've already used the 2, so I advance to the 4. So now I have 4, 3, 5. So I take the minimum of these 3 numbers, which is 3, and then I update these sequences, 6, 9, 15, and the 3 now advances by 1. Now I have 4, 6, 5. And I take the minimum of these 3, which is 4, and then this will update the sequence, so 2, 4, 6, 8, 3, 6, 9, 12, 5, 10, 15, 20. The 4 now is used, so I move up. And now I have 6, 6, 5. So the minimum is 5, so I take the 5. And it goes like that. And each time I take the minimum of the 3 new elements that I have not chosen yet, and I put it in the list, and I update the 3 multiples, and I continue. Okay? And in this way, I will generate this sequence incrementally, starting from 1. Now, this is very easy to program as a lazy program. So let me show you now how to program this. So let me go to the screen here. So the Hamming problem now. So basically, I will define a function times, which takes a string, our list, and a number, multiply
Oops.
L by N. And then I will define merge, which merges two strings, okay, two lists. So merges, so it takes the minimum each time. Huh? So now I can declare H. Let's say H is the sequence of the Hamming sequence. And it starts by 1. And now there's actually I can say how to compute it using these. So I multiply each H by 2, by 3, and by 5, and then I basically merge them together. So the merge is very similar to the merge in a merge sort. So merging two ordered lists will take the minimum element, put it first, and continue. So basically it gives you all of them in increasing order. Okay? So it looks like this. So I do a merge of times L2 and merge of times H3 times H5. So this is it. That's the whole program. Okay? So this program will compute the Hamming sequence. Merge and times will have no limit in size. They're like infinite loops, but they will be lazy. So this is going to be a lazy computation. Okay? So let me define now the merge and the times operation. So times Hn, so that's very easy to define. Is going to be, H is a list. Then call this one S. Times of a string, S of element followed by the rest. So it's going to be E times N followed by times Tn. So this is a very simple definition. So the stream has no end. There's never going to be a nil. So I take an element E, I return E times N. So this is an infinite loop. So if I write it like this, it's not going to be working very well. So let me turn this into a lazy function. And I will also do the merge. Merge function. So here I will do a case, S1, S2 of, so I'm going to take an element from both streams, an element from both, and I will return the merge of the two streams, okay? So let me write it like this, E1, T1, oops, E, E2, E2, like this. So I'm using the vertical bar as a separator, a combining operator. Right? I'm looking at both streams. So the pattern at the right will take one element from S1 and also an element from S2. Okay? And then I will have the merge operation. If E1 is less than E2, then E1 goes to the output, followed by merge of, so I've taken E1, so I put T1, S2, okay? If E1 is greater than E2, then E2 goes to the output, the smallest one, and I keep S1 and I go to T2. And the final case is when E1 is equal to E2. Here I will take, for example, E1, followed by merge T1, T2. Okay? I have to advance in both of them in the last case. If the two elements are the same, like the two 6s here, I only want one 6 in the output, okay? So I will skip both 6s. So you see, this is not exactly the same merge as in merge sort. Because in merge sort, when you merge two lists, if there's two 6s, you have to keep the two 6s in the output, because you can't remove elements in the list. Whereas here, all you want is elements in increasing order, and you don't want duplicates. So if I have two 6s, I will have to skip both of them, okay, and have only one 6 in the output. So if E1 is equal to E2, I have to do the recursive call T1, T2. You see it? How it works, huh? So this is normally how it's going to work. So now we can execute this. So there's two lazy functions and an equation. So I browse H, and I see not much. I see 1 here, because I have created a lazy computation, but I have not asked for any results yet. So when I look at this one here, I create 5 lazy suspensions here. You see that, huh? The 2 calls to merge and 3 calls to times. So if you remember the translation of the lazy functions, so in the blue part, when I execute the blue part, how many threads am I creating then? You tell me. How many? 1,000,000? No. 64? No. How many?
3.
3. Why?
Parce que... non, plutôt 5.
5.
Oui, 5.
So I'm creating 5 threads. So each lazy suspension actually is a thread plus weight needed. Remember how we did the translation, huh? You need to wait. And the unit of weighting is a thread. So if you need a weight needed, if you need something to wait, but you don't want to block the computation, then you need an extra thread. So we translated this using a thread and weight needed. Okay. Note that's the semantics of it. Huh? You don't have to implement it with the thread if you can do a more efficient way. But semantically, it's creating a thread, and inside that thread, it's doing weight needed. So the blue part is going to be executing creating 5 threads. So what happens now if I do browse H.2.1? H.2.1 is actually the second element of the list. Huh? H.2 is going to be the underscore, and .1 gives me the second element. Huh? So this should be returning 2 here. Huh? So when I do that, the computation is going to wake up and it's going to do stuff. Okay? So what H.2 is not going to do anything, because I already have 1 bar underscore. So H.2 will just return the underscore. Okay? But if then I do a .1, I'm asking for the first element in that underscore. And that will cause a weight needed to wake up. In fact, it will cause the weight needed of the first merge to wake up. Okay? The very first merge there will wake up, because the first merge is doing this. The first merge is returning, this merge here is actually returning the underscore. Okay? You see that? That merge that I made in blue, that is what the underscore is. That's the result of that. So when I do H.2.1, it will wake up that merge. And so that merge will execute its body, which is this. And now it's doing a case. S1 is 2, and it will ask for the first element of S1 and the first element of S2. So this merge is asking for the first element of each of its arguments. See how it's working there? I'm executing the, when I wake up the merge, it causes the body, which is the blue part, to execute. And then the case executes, S1, S2, E1, T1, E2, T2, which means I ask for the first element of S1, and I'm asking for the first element of S2. But what is the first element of S1? It's the first argument of merge. It's the result of this. So I'm asking now for the first element of this thing. You see that? Because that's the first argument of merge. So that will cause that times call also to wake up. And the S2 here is asking for E2, T2. But that's the second argument to merge. And this big thing here is the second argument to merge. So that will cause this second merge to wake up. So you see, it's like a chain. Each time I ask for something, I execute the function, and when that function executes, it needs its arguments. So that will cause the argument functions to wake up. So it's like a chain. You see how it works? So the H.2.1 will cause first this merge to wake up. When I execute the body of this merge, it will cause this times and this merge to wake up. And when the second merge executes its body, it will cause these two times to wake up. So all 5 of these lazy functions will wake up. And they will execute one iteration here. They will do one iteration, like this, the body, and then they will do recursive call, here or here, and then they will be a new lazy suspension, the recursive call. So when I ask for one element, all of these functions will execute their body once. And then when they do the recursive call, they will stop again with a new lazy suspension. Okay? So you see, it's how it works, huh? Okay. C'est bon. C'est bizarre parce que le brace H a marché, hein? H. Maintenant ça a marché, okay. So yeah, I must have compiled them in the wrong order, so sorry. So now I can see if I do H.2.1, I have the H goes a little bit farther, 1, 2, and I show the 2, okay. Now if I do touch H10, then I can see 10 elements being created, okay. If I now do touch H100, I will see 100 elements. Okay, let me here we can see over here.
Ouais, c'est comme ça qu'on fait.
You can see them here, huh? The 100 elements goes up to 1,536. And if I want more elements, I can just ask for more elements. And the amount of memory used by this is very limited. I'm only using the memory for the part of the stream that I still have to read for computing the further elements. Okay? And I have always 5 lazy suspensions that are activated. Merge times the 5 calls there will have 5 lazy suspensions. Okay? So the resource consumption of this is very small. So this program, in the 1950s, this was a research question that was published in a journal, how to encode this algorithm, okay? And now I can just show it to you as a small exercise, of course. It's very simple. So the basic equation here is this one. Then I just have to define the merge and the times. Okay? So you see the code is very simple, huh? Okay, let me now show you another example of laziness. Let me now show a really nice example which is called a bounded buffer. An example where I'm combining eager and lazy. And a bounded buffer is something you probably already see. In fact, computing systems use bounded buffers all the time. So let me show you this example. Let me draw first a picture, show you the problem that we're solving. So remember, we have our producer-consumer. Okay, producer-consumer. And there's a stream in there. Okay, and the producer, it's eager. Assume that it's eager. That doesn't, no. It's a producer-consumer, and the producer produces elements, and the consumer asks for elements. So the consumer is in control, and C asks for elements. Asks for an element, and then P will produce the element. Okay? So the way it works is the consumer, whenever it needs an element, it asks the producer for an element. Now that's reasonable, but maybe it's too slow. The consumer asks for an element, and then when it asks for the element, the producer produces the element, and meanwhile, the consumer has to wait. Okay? So the C has to wait. C waits until the element arrives. Okay? So the execution is kind of a co-routening. So if I look at the execution now of this example, I have C and P, and when they do work, so C is doing something, it asks for an element, and then P will compute the element, and when the element exists, it goes back to C. C does some work, it asks for another element, and P will compute the element, and go back to C. So you can see the execution is kind of going in alternation between the two. Okay? C does something, asks for an element, but while P is computing the element, C is not doing anything. And while C is computing, P is not doing anything. So if these are running on two different processors, it's kind of a waste. It's kind of slowing things down. Maybe we could compress, maybe we can make things go a little bit faster. Okay? So that's the role of a bounded buffer. A bounded buffer will improve this, will optimize this. So the second version here is I keep the same producer and the same consumer, and in between I add another component called a bounded buffer. Okay? So the producer, it looks the same. Okay? So the producer sees no change. And the consumer thinks it's looking at the producer. The consumer also sees no change. So this component is completely modular. You can put it in, you can take it out, and the producer and the consumer, the code does not change. Okay? The bounded buffer has the same interface here as the consumer, and on the output it has the same interface as the producer. So to the consumer it looks like a producer, to the producer it looks like a consumer. Okay? But it has a very special operation, this bounded buffer. The bounded buffer has a size. it has memory allocated to store n elements. N elements of the string. Okay? So when the system starts up, and the consumer does not ask yet, the bounded buffer will immediately ask for n elements from the producer. Immediately. Even if the consumer has not asked for anything. So the producer will actually do eager execution for n elements until the buffer is full. So the producer will produce n elements. They all get stored in the buffer. And when the consumer asks for an element, the bounded buffer can give it right away. Boom. Doesn't have to wait. So if there's 10 elements in here, for example, then when the system starts up, the producers will immediately compute 10 elements. And the bounded buffer is full with 10 elements. And if the consumer asks for an element later, it will immediately get it because it's already computed. Okay? It doesn't have to wait. That means the consumer will be faster. Also, the producer will have less idle time. It will be going ahead of the consumer. The producer will be computing more elements than the consumer is asking for right away. So the producer is less idle, and the consumer has to wait less. So we have improved the performance of the system, okay? With this. We've improved the performance just by adding this component. Transparently, by adding that, we do not change the code, producer and consumer. We add this component and the performance is improved. Okay? Very good. That's great. Well, this bounded buffer is actually a combination of eager and lazy computation. Okay? So when the bounded buffer starts up, when the producer starts executing, the bounded buffer has started and the producer starts, then it will execute eagerly, it will keep computing. So the producer will produce n elements until the bounded buffer is full, and then it stops. And then it becomes lazy. Okay? So the producer will be eager until the buffer is full. And then it becomes lazy again. And if the consumer takes elements out of the buffer, the producer will become eager again. So the system will alternate between, the producer will alternate between eager and lazy. Okay? It starts eager, but only for n elements, and then it becomes lazy. So it's kind of a combination of eager and lazy. Okay? So this bounded buffer is a very useful thing, and probably you've seen it already. Huh? In every computer system will use this. But it's hard to understand what it precisely means. In fact, it's declarative. It's completely declarative, does not require updating variables, and it's actually doing lazy deterministic data flow, a bounded buffer. So I'm going to show you how to design, to code this bounded buffer. Okay? So let me show you now. Bounded buffer is a typical example of combining eager and lazy computation. So let me first do a simple producer-consumer. And then we build, so first I will program the producer-consumer, and then the bounded buffer will program it so you can stick it in the middle. Okay? So the simple producer-consumer. So let me, it'll be very prod n. Let me pretend that the producer is doing a lot of work. So here's a producer. I put in a delay. So it's creating integers, 1, 2, 3, 4, forever. But I put in a delay of 500 milliseconds so that you can, so it slows it down so we can actually see the execution. So assuming that each of those elements takes a lot of computation, so the producer is is working for 500 milliseconds. Okay? And now let's make a consumer. Let me say that the consumer is doing an accumulating sum. It takes a stream S. And it returns the accumulating sum of this. So it's like this, H plus X. And N. So the consumer actually has an output here. It's accumulating things. So if the stream is 1, 2, 3, 4, the consumer will output 1, 3, 6, 10 on the accumulations. And they're both lazy. Okay? So now I can show you how it executes. So here's this execution. So I will take two streams. So S1 will be the producer stream, and S2 will be the output of the consumer. Like this. So when I run this, both of these functions are lazy, okay? So it's not going to display anything yet. I will only do work if I ask for results. Huh? Sorry, I was in the wrong Aquamax mode here. Oh, I'm in a weird mode here. Previous element mentioned. Ah. Okay, fine. I'm out of it. Sorry, when I type very quickly, sometimes Aquamax thinks I'm doing something. Okay, let me like this. Yeah, okay, so I've actually executed it several times. Just look at the last two underscores, that's S1 and S2. Okay, and now I can do something. I can say, for example, touch, S2, 5. I want 5 elements. See how it works? See, it's taking some time, huh? 500 milliseconds. So duck, 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 taking some time there. And if I do more elements, see, each 500 milliseconds it's adding one more element, and the second one is the accumulating sum. Okay? So this is a standard producer consumer with no bounded buffer. Whenever the consumer needs something, it asks the producer. Now let's try to improve the performance by adding a bounded buffer. So we have to define the bounded buffer. Okay? So let me define the bounded buffer in steps. We'll refine it. Refine it in steps. Okay, so here is the bounded buffer. S1, S2, N is the size. Okay, so the bounded buffer will look like this. It's a procedure. That's S1 as input stream, S2 as an output stream, and the size. So it's not, I'm not writing it as a function because it has these two streams, okay, an input and an output. So this is the bounded buffer component. Okay, it looks like that. So how am I going to write it? Well, the bounded buffer, first of all, it does not change the results. The S2 is the same as S1. So the basic bounded buffer is just going to pass the input to the output, okay? So the first step I'm going to do is just passing that, doing that. So this is the first step, this one. Let me show you now the second step. Okay, and now I will have the basic operation. I will start by just passing the elements from input to the output. So like Noah, a loop. So let me make a lazy loop that takes a stream, then reads the stream, and passes it to the output, with doing nothing, okay? And then we will improve that to make the bounded buffer. So the S2 is loop S1. This is the beginning of our bounded buffer. So far it's not doing the bounded buffer yet, but this is the first part of the design. So the loop here is reading S1 and is passing the elements to the output. So it's not changing anything. So this is like Noah, okay? This loop is not doing anything. And now, in order to make a bounded buffer, we're going to add stuff to this loop. We're going to make it do more. We're going to make it do the work of a bounded buffer, okay? So how do we do that? Well, when the system starts up, okay? When the system starts up, the bounded buffer immediately has to ask for n elements from P, okay? So in this version, it's not doing that yet. So we have to add something where when I call the bounded buffer for the first time, it asks for n elements, okay? So let me take this code, and we'll make a third step now. So step by step, so you can see exactly how we're doing it. So now we actually have to add elements, okay? So here, for example, I'm going to use this list.drop function. I'm not going to define it. It's part of the library, okay? And you have to define end, of course. So this function here will remove n elements from S1 and return the resulting end, okay? So what happens here is that it asks for n elements whenever it starts up, okay? So I'll write down what's doing. Ask for n elements at startup. That's the first part, okay? Or the third step. The previous step is actually just doing passing elements from in to out. Not doing anything. Third step, ask for n elements at startup, okay? But that's not enough. We have to do a little bit more than that, because when the consumer asks for one element from the bounded buffer, then it's not full anymore. Then there's n minus 1. And so the bounded buffer has to ask for another element. So we have to ask for n elements at the startup, but each time the consumer removes an element, we have to ask for one more element. Okay? So we have to do a little bit more than this. So let me go a little bit farther. So we make the fourth step. Whenever consumer asks, so ask whenever consumer asks. Ask for one element when consumer asks for an element. Okay? So here's the code. What that means, this is the consumer is actually the reading loop. Okay? So that means we have to take this end argument and pass it to the loop. Okay, like this. So whenever the consumer asks for an element, then I will actually execute this. Whenever the consumer asks for an element, the lazy suspension loop will start, and it will execute the body, loop, and it will return H1. But also, at the same time, I have to ask the producer for another element. Well, that's by using end, okay? Basically, I put end dot 2 here. So you can see here, in the blue part, it's asking for n elements on startup. And in this second blue part, it will ask for one more element each time the consumer asks for an element. So end is always n elements farther down than S1. I have S1 and end is already list drop. It's n elements farther. So if I ask for one element from S1, then I need to ask for one element from end. End is going to the producer. Okay? So that's almost done. Now we're almost done. See how we're building it, kind of step by step. Now it's almost done, not completely done, because we are blocking the execution. This blue part, it's a sequential code. It will actually wait until it has dropped n elements from end. So it will block the whole execution of the bounded buffer. So how do we solve that? When we have a piece of blocking code in deterministic data flow, it's very simple. What do? We put it in a thread. So the final step is putting it in a thread, and then we're done. And we have a bounded buffer. Fifth step, put producer asks in their own thread. So this has to be put in its own thread. And also this one has to be put in its own thread, but that's easy. Like that. So now we have a complete running, working bounded buffer. Okay. Yeah, I think it's all completely correct now. Nothing wrong. This is a correct bounded buffer using lazy deterministic data flow. Now we can actually run it. Okay, let me compile this. By the way, if you see a bug, you have to yell, because sometimes I make bugs. I know it's hard to believe, but it happens. Okay, so I do this. Now let me take the original program here and put the bounded buffer in the middle. So I take this one. Now I will have the execution with bounded buffer. I will now put a bounded buffer in the middle there. So the way to do that is I will now have a third stream, S3, S1, I will have S2 bounded buffer, S1, S2. Let me make a small bounded buffer of size 3. This one now returns S2, it's S3, like this. You do like this. And let me show the 2 to 3 streams here. So basically it's the same code as before. You can see producer, consumer. It's exactly the same. I just stick the bounded buffer in the middle. Okay? You can see it there. No hand waving. It's exactly what I'm doing. And if there's no bugs, it should work. So I make a small buffer of size 3. Okay? So what happens? So look what happens. S1 is actually the producer stream. Notice it has computed 3 elements. Okay? And S3 is the output of the consumer. So if I ask for one element now, touch S3 1, then the consumer will immediately return back. There's no wait. Huh? There was no 500 millisecond delay, and the producer immediately calculates then the fourth element. You see that? If I now ask for 5 elements, here, 5 elements in all. So there's already 1. So 4 more elements. 3 of the elements, I can give them immediately. Okay? Let me do a little bit more to make it clear. Do 8. So I'm asking for 8. I already have computed 1. So I need to get 7 more elements. 3 of them already exist. 2, 3, 4. I will get them immediately. The other 4, I will have to wait 500 milliseconds. So the bounded buffer has sped up the system, has made the system faster. So you can see what happened there? So the 2, 3, 4 immediately appeared on the output. 5, 6, 7, 8 appeared a little bit later. And then the producer goes even a little bit farther, 9, 10, 11. Because it always tries to stay ahead by 3, okay? So the producer will be eager until the bounded buffer is full. So you see how it works, huh? This is actually a fairly subtle example of a program that uses lazy deterministic data flow. And with this bounded buffer, you can see it's completely declarative. People don't believe when you tell them that a bounded buffer is declarative. Usually bounded buffers are written with arrays and their assignment, state. But in fact, a bounded buffer is a completely declarative component that is a combination of eager and lazy. Okay? So this is already a more sophisticated example of programming with eager and lazy. Huh? Okay, let me stop there. Let me stop here for today. So normally so the next week lab will be all about laziness, okay? Lazy, so it's important to understand how the laziness works the way it needed, but also the thing is that you could use it in any languages. So the advantage of doing laziness in a language like Oz is that the code is very compact. So you don't have to worry about handling all kinds of boilerplate. But then, once you understand the algorithm, you can program it in any language. Okay? So laziness is very important in any programming language. But it's important to understand the basic idea. Okay? So let me stop there.